പ്രോഗ്രാം നല്ല റെസ്പോൺസ് ആയിരുന്നു. ഒരു വലിയ
ഗൂഗിൾ മീറ്റിൽ നിയർലി 120.
ഓക്കെ ഓക്കെ
വിളിക്കുകയും ചെയ്യാം.
ഞാൻ സുരേഷ് പിള്ളയ്ക്ക് ഫോർവേഡ് ചെയ്തിട്ടുണ്ടായിരുന്നു.
ഓക്കെ.
യുവർമ്മ സാർ ഓഫീസിലാണോ അതോ വീട്ടിലാണോ?
വീട്ടിലാ സാറേ.
ഓക്കെ ഓക്കെ. Thank you, sir. Thank you for agreeing for this lecture.
You're welcome, sir.
With your very, very busy schedule.
It's okay, sir.
Sir, yes, please.
Okay, I think we can start now. Now it is 3 o'clock. Very warm welcome to all of you for this webinar session. This is session 5 of this webinar series. So we were successfully completed four webinars related to chemistry. So today we have a different topic which is related to our environment, and also it is related to our spectroscopic techniques. And here we have our dear Professor Dr. Ravi Varma from Physics Department to deliver the speech today. Sir, a warm welcome to you for this webinar session. And another personality here is Devadasan sir. He was actually with us for a long time here in NIT Calicut also as a guest faculty. And in Calicut and all over the Kerala is very familiar by his social few words about that. From St. Thomas College, Thrissur, and did MPhil and PhD from Calicut University. He was a professor at Malabar Christian College, Calicut for a very long time. He joined Malabar Christian College in 1975. And he retired in 2008. He was also served as head of the Department of Chemistry long time. And he is also associated with the National Institute of Technology, Calicut. 2 years he were with us. He is with us as a guest faculty in Department of Chemistry. He was also served as a Dean of Science and Humanities at KMCT Engineering College, Manasheri. And his social works involved the activities in Kerala Shastra Sahitya Parishat and Society for the Protection of Environment Kerala. He was also a chief mentor of Innovation Hub, Regional Science Center and Planetarium. So Innovation Hub is actually for motivating the school students, especially the high school students. He is now working as a secretary of Calicut Chemistry Collective Forum this is actually a forum of college teachers, and recently we had a very good webinar by Dr. Renowned scientist Dr. Ajay Ghosh. So I think a large number of participants were there. So he is actively working in this type of social platforms also. Sir, I welcome to this webinar session, and I invite you to chair the session also, and you can also introduce our speaker, Dr. M.K. Ravi Varma. Sir, please. Please, sir.
Thank you, Dr. for your kind words of introduction. I am indeed very happy to be a part of this webinar series. A very good afternoon to all. It is indeed a matter of great pleasure to me to introduce to you the speaker of today, session 5 of the webinar series, Dr. Ravi Varma of the Department of Physics, NIT Calicut. Dr. Ravi Varma MK did his master's in physics, specializing in advanced particle physics at the University of Hyderabad in 1995. And then a graduate research assistant in the Department of Atmospheric and Oceanic Sciences at the University, Montreal, Canada, during 1996-98, and was awarded Masters in Atmospheric Sciences, Atmospheric and Oceanic Sciences from the same university in 1999. And then he took up graduate research assistantship in the Division of Atmospheric Sciences, Research Institute, Reno, Nevada, United States of America, and was awarded PhD in Atmospheric Sciences from the same institute in 2003. He was with the Irish Environment Protection Agency, was his postdoctoral fellowship during 2006 to 2008, and again during 2008 to 2009. He is currently working as professor in the Department of Physics, NIT Calicut, and his main area of research is applied optics and instrumentation for materials and their characterization, especially for air pollution monitoring and climate applications. Monitoring greenhouse gases and airborne aerosols by using optical and spectroscopic techniques. He had vast experience of managing developmental and field monitoring campaigns during his stay in United States for the United States Environment Protection Agency and the US Department of Defense. He has more than 10 years of teaching experience and has published many technical reports and research articles in peer-reviewed journals. He is a visiting researcher in many universities abroad, in Ireland, USA, China, and Japan. He is also the chairman of the Institute Innovation Group, National Institute of Technology, Calicut. So indeed a matter of great pleasure, you sir, to invite for a lecture in this webinar series. The lecture title, Spectroscopic Measurements of Atmospheric Trace Pollutants. On behalf of all those present in the webinar, I extend to you, sir, a very warm welcome, and may I now invite you for giving the lecture. Thank you.
Thank you very much, sir, for the kind introduction. I will now share my PowerPoint presentation, I suppose. Let me try. Is it visible?
Yes, they are visible. You can expand.
Now?
Yes.
Okay. Okay. Thank you very much. And topic of my lecture today is spectroscopic measurements of atmospheric trace gases. I am not a chemist, and I am giving you a lecture in chemistry department. However, most of the applications of spectroscopy that we do have something to do with chemistry. Although I'm not going to talk much chemistry about in the projects that we are handling, I will try to keep an instrumentation point of view throughout the lecture and try to present one or two or three techniques that we have adopted over the past 20 years in monitoring atmospheric trace species. With that, I am going to begin my lecture. First, we will take a quick look at what trace gases are and why we need to make measurements of these trace gases with high sensitivity. Then I would move on to and most of the or the biggest application is using Fourier Transform Infrared Spectrometer. I will tell you why, and I will give you some basics regarding that instrument, and that will be useful for most of the chemists here as well, because material scientists also use a lot of FTIR spectroscopy for validating their research and materials, so it might be useful. Then I would use the FTIR and demonstrate some of the projects we did, how we make measurements in situ measurement in the atmosphere, meaning it's a non-invasive measurement without touching the sample, and then and there measurements by sending the light into the atmosphere. So that we call it open path measurements, and because of that we are sending the light to the atmosphere and then we are trying to measure the light. We call it optical remote sensing also. Now with the invent of optical remote sensing, we could not only measure the trace gases in the atmosphere, we could also try the information that we get from optical remote sensing instruments to characterize the emission sources. For example, if you have a landfill somewhere, then it will emit a lot of methane. It's a greenhouse gas. Could we actually go to a landfill and use these optical measurements and pinpoint where actually the gas is leaking? It can be in other industrial facilities too. So we could really apply this into finding the emission sources, also measuring number of grams per seconds or gram per hour of emissions from that sources. So these are the important aspects that people are looking for in environmental science also. So after that, infrared spectroscopy, I will go into UV visible near infrared spectroscopy. For that, I will take a small desktop kind of instrument, which is not in the open path, which is an extractive instrument, and then talk a little bit about the theory and then application of that. That's called cavity enhanced absorption spectrometer. So what are trace gases? So in order to understand that, we need to take a big picture. And in the big picture of the Earth's climate system, it has a lot of components in it. First and foremost component is the let me see if I can get disappointed. So first and foremost is the sun, which gives us all the energy that we need. Everything and everything happens on the Earth. The energy comes from the sun, and it comes on top of the atmosphere, and some of it is lost in the atmosphere, some of it reaches the surface of the Earth, some of it is absorbed there, some of it goes back to the space. So total amount of energy coming into the Earth system must be equal to the total energy that is going out. Otherwise, we will not be in a climate equilibrium. We will either, depending upon the budget, whether it is positive or negative, we will be moving our climate system either to the hotter or colder climate conditions. So, a lot of things: sun, atmosphere, oceans, land, vegetation. Among that, you can see atmosphere contains primarily nitrogen, oxygen, and 1% of argon. Anything other than that is considered as a trace gas, and of which some of them are really important. For example, CO2 is a greenhouse gas, methane, CH4 is a greenhouse gas, N2O is a greenhouse gas, ozone protects us from UV if that is in the stratosphere. It is a poisonous gas in the stratosphere, which is formulated from the vehicular emissions. Then we have a lot of particulate matter called aerosol. We have water vapor in the atmosphere, which is also greenhouse gas in some sense. So you can see that a lot of gaseous particles are there. Not particles, gaseous compounds are there in the atmosphere. Some of them are really highly reactive. For example, some radicals, the oxidants. For example, OH is a radical. That is the primary oxidant, daytime oxidant in the atmosphere, and NO3 is a radical, which is the primary nighttime oxidant. So they are highly reactive, and they are also sensitive to the light. So there is some photochemistry there. So even though these radicals, for example, NO3, nitric radical, is present only for 5 seconds, it can trigger a lot of reactions. And it can oxidize a lot of compounds, and it can trigger things like acid rain, etc. Or nitrous acid, HNO2, also called HONO. Also, so many of these compounds, the reactions in the laboratory and the reactions in a very large system like atmosphere. Of course, the chemistry is the same, but the system is the size of the system is different. So sometimes the study is also in any case, whether they are present or not is something puzzles. So people propose some reactions, some intermediate compounds, and the way they validate this are by measuring those intermediate compounds using some techniques. Nitrate radicals cannot be chemically detected, because by the time you collect it and bring it to the lab, they may have already gone into different compounds. So you have to use some sort of an optical technique, a spectroscopic technique, to measure the presence of this compound. So I think trace gases are important, and they fit well in the big picture. How do we do spectroscopy? So if you look at if you are a physicist, you know that if you take 5,250 degrees Celsius as a temperature of the sun, then you can see the black curve gives you the black body emission spectrum using Planck's radiation law. And the yellow one here actually indicates what is measured on top of the atmosphere. So they're pretty well, quite well fitting. Now when you come to the sea level and you measure again, you see what is red. Now you see difference between red and the yellow actually gives you the difference, gives you what is lost in the atmosphere. So takes everything below 350, takes out everything below 350, so large part of the radiation is gone. protects us very well. And then you can see that a lot of light is lost due to scattering. Of course, the peak of the solar spectrum is invisible. So then you can see a little small dips along the red envelope. So they are the absorption spectra of different compounds. There is a water band and CO2 band. There are several water bands. So those lights are totally absorbed in the atmosphere. Those bands have high water absorption cross section, so they are completely gone. And you can see some of them are very high. So you can use this information, the absorption information of each molecule in the atmosphere, and then you can actually study their presence. So this is the fundamental aspect of the spectroscopy. What do we do usually in spectroscopy? We will have a light source, whether that can be a monochromatic light source like a laser, having one single wavelength emission, and then you have a detector which detects that. You could also have a spectrum of light, like visible or infrared light or near infrared light, UV light. Now that travels through full distance and reaches the detector. Now, if you have something in between, a volume, a sampling volume, so if light is absorbed there, then you know that the target sample is there. So you look at the spectrum, or you look at the absorption or the loss of light in the monochromatic wavelength, you can say the target compound is there or not. So what is the underlying principle? The underlying principle is Beer's law, or we call it Beer-Lambert law or Lambert-Beer-Boucher law. So three people are responsible for that. But in short, it is known as Beer's law. So what does it say? If you have the light intensity coming, passing through a sample of length, the length that it travels through the sample is B, and it exits at a different intensity. E is the power which corresponds to the intensity of the light that we measure. So T is the transmission, A is the absorbance. So there are two things. One is absorbance, and then there is absorption coefficient. There is path length. So transmitted light is e to the power minus alpha b. This is the physics point of view. And in chemistry, mostly they use the logarithm base 10. So it should be 10 to the power. So in which case there will be a log 10. Absorbance is given by log of 1 over transmission, which is in chemistry many times we use log 10 base. The difference is only a factor of 2.303. So it doesn't matter. But in physics, you can see that it commonly is written in the exponential base. So this is Beer-Lambert law. That's it. Transmitted light is e to the power minus alpha b. It's simple. As simple as that. So, this is conventional spectroscopy. In conventional spectroscopy, you can see that there's a light source, there's a detector, and the space in between as the sampling volume of the target pollutants. So, you can have two ways. One is you have a sample in a container, maybe a cuvette or maybe a little volume or something like that, or you can have an open path system, like we just send it to the atmosphere. So either way works fine. Now, one other thing you will notice is that the path length is important. If absorption coefficient is very small, the longer it travels through the sample, the better chance that you detect it. So traveling path length is important, and the absorption coefficient is important, which in turn depends on the number of molecules and the absorption cross section. So when you pull the sample through a volume, it is called an extractive system. I am only talking about the air samples. We are not talking about any liquid samples here. So if the air sample is pulled through a system, then it's called an extractive. Or if you simply not pulling the sample, it is sent through the sample and checked on the other side, that is open path configuration. So one is an extractive configuration, one is open tap configuration. So depending on the technology and the pollutant of interest or applications, we can have both. I will give you example of both. Moving forward, conventional optical spectroscopy for the atmosphere. As I said, these trace gases are very, very, very small in number. Meaning, if you take, parts per million means a million molecules, 1 in a million molecules. Part per billion is 1 in a billion molecules, and billion is 100 crore. And parts per trillion is even 1,000 of that. So you can see that nitrate radical are very, very important, even if they are seen in 1 parts per trillion. So you can see that 1 molecule out of a trillion, so it's very, very hard to determine. So how do we improve the sensitivity of the instrument so that you get enough absorption signal above the noise of your instrument? You increase the path length. So in order to increase the path length, people try to find appropriate light sources and detectors. So tunable diode lasers, that means that is a laser. You tune the current, it will go over 1 absorption line of a molecule, target molecule. So since they are lasers, they can travel 1 kilometer or 2 kilometer path length. So tunable diode lasers are used in the near and mid-infrared spectral regions. Similarly, ultraviolet and visible ranges, you have differential optical absorption spectrometer. We are not going to go into that. All these compounds are not very relevant. I just showed you so to demonstrate that you can have instruments that have a sampling length of several kilometers. You see, so your sample volume is such a huge volume. It has its own this thing. That's different. So you have a long path length. A very long path length will allow you to have enough absorption of the light that is sent out so that you can have some minimum level of detection. So increasing the path length is obviously one of the ways to improve the detection sensitivity of the instrument. Now, other than these 2 instruments for atmospheric applications, I'm talking only about atmospheric applications. We use conventional Fourier Transform spectrometers. So you can see that since they are all already sending the light into the atmosphere and they're detecting the light either return back or reflect on the other side, that's called optical remote sensing. And they are also called path integrated optical sensing because they measure the intensity or they measure the number in the integrated in the column of the air that measure. So they call path integrated optical remote sensing. So before we go into the spectrometer, we do use this approach ourselves. So we recently made some measurements in Shanghai where we have 2 laser beams very close in wavelength sitting on 6th floor or 7th floor of the building, university building, and we shot it across a major highway. So this is about 650 meter one way, 1,300 meter return. We are looking for just 1 molecule, that is nitrogen dioxide. Nitrogen dioxide is an important molecule, NO2, and it is responsible for the photochemical interaction, production of the ozone. Along with ozone, NO2 will produce nitrate radical also. So the pollution level of knowing NO2 is very important, and that is a major pollutant. NO and NO2 are a major pollutant coming from vehicular activities, and you can see that we are trying to measure over a major highway. But with this, we could see that we have a very good detection sensitivity. 2 parts per billion by volume is the detection limit. And we have measured up to 120 parts per billion. And these measurements are an integration time of about 30 seconds. So you can see that a lot of things. And we also have a chemiluminescent detector, which is it's actually not industry standard, but it's actually widely used. Chemiluminescent detectors. We use 30 minutes because chemiluminescent detection needs that much integration time for a proper measurement. So you can see that a point measurement and this corresponds very well, especially when we actually use 2 weeks of measurements, and we averaged 2 weeks of measurements for every hour representing the day, and you can see that the black one. is our measurements, and the red one is actually chemiluminescent detector. So we can see that very well, and since we shoot our light across the highway, you can see that the highway traffic starts early morning 6 o'clock. We start seeing the traffic earlier than chemiluminescent detector because pollutant takes time to reach the building. Chemiluminescent detector is an extractive instrument. It has to pull the air into its sampling volume, and it takes time for reaching that first. So that was one of the optical remote sensing measurements that we did. Now coming to Fourier Transform Infrared Spectrometer, you can see that it's a Michelson interferometer. I first apologize for an error that I made. This is actually, it should be like that. But never mind. So light goes with a beam splitter, splits into two. One goes to one mirror, the other goes to other mirror, and both return to a detector. And this is the Michelson interferometer. Michelson's interferometer was originally proposed for trying to detect ether as a medium in which light is propagated. It's all about the study of light, whether it's particle or wave. Now, what happened is that they didn't detect either. So Michelson's interferometer was actually not successful. Nevertheless, Michelson got a Nobel Prize. So maybe the only Nobel Prize for a negative result. However, his instrument was very clever, very useful, and it forms the basis of Fourier Transform Infrared Spectrometer. So what is there? What is the difference between a normal Michelson interferometer and an FPIR? First, we have one of the mirror that is kept as a moving mirror. So a mirror can move back and forth about 20 centimeters. That's, I think, the industry standard, 20 or 22 centimeters. I'm not exactly sure. So it keeps moving back and forth, and then we have an infrared light sent, and then it do the same, reach the detector. And what happens? If you have a single wavelength, a monochromatic light, then you will get fringes, just like Michelson models experiment, you will get the fringes. If you have single sinusoidal wave, you get bright and dark fringes. Now, instead of that, if you use a broad spectrum which contains all wavelengths, small wavelength, high frequency, long wavelength, short frequency, what will happen is that you will get, as the mirror moves, this is the distance, 20 centimeter, and this is corresponding distance. So as the mirror moves, what happens is that it moves and intensity have a profile like that. And that is called an interferogram. So this is the basic measurement principle of Fourier Transform Spectrometer. So what is the information that we get from that? So we go to another schematic. We have a Michelson interferometer, and we have a moving mirror. And then you can keep the sample cell in one of the beams, and then you get an interferogram. What do we do with the interferogram? We take a Fourier transformation of the interferogram. So what happens is that the x-axis is distance. So we'll get the x-axis in wave number in the Fourier space. So that is 2 pi by lambda wavelength, and this is intensity, some sort of a scale intensity. So you can see that it actually takes the spectrum of the lamp, and in the sample, whatever is absorbed, that lines shows up. So the intensity is showing up. So Fourier Transform Spectrometer is a beautiful instrument, and it, with a 20 centimeter long mirror movement, it can actually go from 400 to 4000 wave number, which correspond to 2 micrometer to 20 micrometer in wavelength. So that's a broad wavelength. And this 20 centimeter is not what is the significance of the mirror movement length? The larger distance it moves, higher resolution the spectrum will have, because it's a Fourier transform. So in material chemistry, people usually use 4 wave number measurements. So that's a shorter distance. And people doing high-end spectroscopy needs 0.5 or 0.01 centimeter inverse or number resolution. They must be moving a lot of length, meter or even multiple meters. So increasing the length of the mirror movement increases the resolution. Okay, now what do we do with that? We made an instrument. This is actually when I was working in Cadis Incorporated USA immediately after my PhD. So we developed a sort of instrumentation for our purposes. So this is the Fourier Transform Infrared, and we want to send the light out into the atmosphere and bring it back. So we use a 12-inch big telescope. Otherwise, light collected will be less. So all the little box in the top is our Fourier Transform Infrared. Everything is there. And then from there, we put the data into a trailer. So this is for open path air pollution monitoring. What did we do? So I'll show you a small example of what we do with these open path measurements. It not only measures what is in the atmosphere, but also it can be used for other purposes. So we try to demonstrate. FTR makes 300 or more compounds. So I'm not going to go into that. So we try to use it to characterize the sources. We try to find the emission source location, and we try to measure the emission rate from the sources. So we try to do it by actually releasing a gas. So how we do that? First we set it up. So we put a lot of retro-reflecting mirrors. We send light. First we mounted the instrument onto a scanner. We sequentially scan the whole area with, you see, one after the other, after the other, after the other. And then we scan the whole area. This is a small area. This is for demonstration. You can see a gas cylinder there. We release the gas cylinder, some gases, and we try to see some gas is there, some gas is there. So we try to release the gas. So this actually happened just before I joined the institute and that company. Okay. So we try to scan and we try to see where we actually emit the gases. So FTIR is very powerful. We could do that. So we have three configurations. The one we see is scanning horizontally, that will locate the plume. Then we can scan vertically, that will tell you how much is emitted downwind of the emission source. So these are all the, we mathematical formulation of the area. We split the area into different pixels. Each pixel will have one retroreflector, and then retroreflector is nothing but if you send the light to your retroreflector, it returns it back to the source. So we have the source and the detector at the same place. At one location, and we found gas there, about 17 meter. So this is by scanning the whole area with the 9 different locations. So it's not a very high resolution measurement, yet we were able to find the gas. So we did apply it to an industrial water treatment facility. Industrial wastewater treatment facility. So we had an instrument. We have several. We used the whole area. We made different pixels. We locate the reflectors wherever it is possible, and we seek for any potential harmful gases. So these are all demonstration projects. It's heptane emitting from that part. Heptane emitting from different locations. So you see, we not only can line simply shows the optical path of measurements that we made, and then we use an algorithm to interpolate and predict the locations that are available. So when you do a vertical scanning, you put a scissor jack about 10 to 18 meters high, and then you do that, and you have to set up it at the downwind location where you carry the pollutions into these beams. If you set it up on the upwind, of course you will not measure. So that's a little tricky part. Many times after we set up, the wind changes and we will never measure it. So look at that. So this is a scissor lift, and we can set up. So these are not light sources. These are flash from camera. You can see that the light will return back to the camera. So these are called retro-reflecting mirrors. It reflects the light exactly to the same direction, opposite direction here. So we actually did the ethylene release in that setup, and we did 0.11 gram per second release, and we retrieved 1.103 grams. And so you can see that these kind of techniques and the simple algorithms can have very good impact on environmental monitoring. So I'm not going to go into that detail. So this is also another landfill. So we can split into different areas and we can make a measurement. So this kind of approach also. You can see methane emissions, also 320 parts per million, so huge methane emission from that land. So we did this experiments for US EPA on some of the landfills in the Department of Defense facilities. Along a railway track, I showed earlier, but opposite to the railway track, there are a lot of industrial plants. So we found coming from this facility and methanol coming from this facility. So we optical remote sensing for meaningful measurements and characterizing the sources and giving more information about such emissions and location of such emissions. Having said that, I will go to the second part of the talk, which is UV visible spectroscopy. UV visible spectroscopy is more, IR is more into the vibrational and rotationally modified spectrum, the fingerprint regions of the spectrum, whereas visible mostly deal with the molecular transitions. So if you look at the nitrogen species, so this is just nitrogen species in the atmosphere: nitrous acid, nitrogen dioxide, and the nitric acid. NO is not in this region, so I will not do that. Measuring NO, there are other techniques too that are adapted. Other set of are I will come to one of the applications where I will explain why iodine is important. When you have chlorine compounds and bromine compounds, they are also important in the atmosphere. There are a lot of bromine oxide emissions. They are also found in Ran of Kutch in Gujarat. They are all mostly geological emissions, and it has been found in satellite, but we have not done any real ground measurements there. It's also found in Arctic circle. So bromine, they are all geological emissions, we suppose. So everything together. Now, how do we use this information? So we developed a different spectrometer. Here, like I said, very small amount of trace gases are available in the atmosphere for measurements. So you have to increase the path length. So we say something called incoherent broadband cavity enhanced absorption spectrometer. Incoherent means a broad spectrum of light. It's not a coherent laser emission. So the reason for adopting this is to have high detection sensitivity, high temporal resolution, and high spatial resolution. Open path measurements will only get you the column indicator density, and if you have a localized emissions, you're actually losing the edge of. And incoherent also means multi-component detection capability.
Sir, can I?
Now, yeah.
Actually,
Yes.
Sir, you are not seen on the screen. On the screen.
Okay.
You are not seen on the screen.
Okay. Okay. Now it's okay. Okay. Now I'm okay.
Okay, so
Okay.
thank you.
Yeah. So like conventional spectroscopy, you have a broad or a light source, and you have a detector. In this case, is a grating detector, and then you have a sampling volume in between. The only difference with conventional spectroscopy is that you have two high reflecting that creates an optical cavity, or called optical resonator. It's nothing but high reflecting mirror, so it keeps back several times before it goes to the detector. So you can increase the light, increase the length of that light travels through the sample. So for that we use an optical resonator. So how do we do that? How do we increase the optical path length in a meter long or even less sampling length? So this part I will not explain in detail because it's the mathematical derivation part, but I will simply go through what is happening. So it's a conventional spectroscopy where you have nothing in there, will give you I naught. If sample is there, it will give you I. So you have an I in and I out. No sample, I gives you I naught. With sample, I gives you I. So L is the loss, goes from 0 to 1. L equal to 1 means everything is lost. L equal to 0 means nothing is lost. So this is the convention. So just one path. So you simply add a Beer-Lambert law and expand the exponential component and take only the first, all the higher orders are omitted, and then you will get, you will get, you will get an equation. Absorption coefficient is equal to 1 over D. D is the path length of the sample. I naught is the spectrum with the sample in it. A very simple equation. This is a Beer-Lambert's law in a different format. That's it. 1 by D, I0 over I minus 1. Perfect. Now, when absorption losses are very small, you do this exponential approximation of the exponential series, retaining only the first term. That's a mathematical part of it. We are not going to do that. What will happen when you add cavity on both sides? The same thing, cavity on both sides. What happens is that you send the light, part of the light goes in. I mean, if it is 99% reflectivity, 99% light is lost, only 0.1% light goes in, 0.1% of that goes out. 99% of that reflects back. So it goes back and forth every time, leaking a little bit to the output. So 1 pass, 3 pass, 5 pass, 9 pass, like that it goes. And you can always reflectivity goes from 0 to 1. 0 means nothing reflected, 1 means everything reflected. Something like glass. So you can put all those terms in it and you can keep adding and adding and adding. Finally, you will get a geometrical series, and of course, R is less than 1 and D is less than 1. You will end up with a equation that we can deal with. So do not worry about the equations. All we are trying to do here is that we increase the path length of the light through the sample so that a very little absorbent in this sample can also be detected because light passes that many times through. That's the increasing the path length through the sample by using a stable optical cavity. So you use this, try to do that again, the same mathematical formulation of Beer-Lambert law, and you get big equations. Do not worry about it. You approximate it for very low absorption. That's where we need more sensitivity, and then you get an equation like that. You can see alpha is 1 by D, I0 by I minus 1. So this is if you have single pass, and you have an addition term 1 minus R if you have multiple pass. R is nothing but the reflectivity, and if R is 99.9% reflective mirror, meaning 1 minus R is 1 minus 0.999 is 0.0, that is 0.001. So you can see that R is an important requirement, which means any instrument you make with that should have a proper knowledge of the R. That's it. This is all theory of the instrument. I skipped it too because I think it's not too important to know the theory now. Now, what do we do with that? As I said earlier, iodine is an important compound in the atmosphere, particularly marine boundary layer, especially in higher latitudes. So this particular development happened when we were when I was in Ireland. So what happened is that we noticed a few measurements and a publication saying that the iodine emission was found high when immediately after the full moon day. That means after every tide, iodine emission is high. So that was puzzling to many people, and the botanists collected some special kind of microalgae. These are seaweeds, and they found that one particular species of the seaweed has 1% of its dry weight as iodine. That's a lot of iodine in one particular marine species. So a lot of chemistry there and a lot of photochemistry there that is related to iodine, which again I am not qualified to go into that chemistry. Besides that, iodine emissions are important. Can you measure iodine? A lot of iodine, I said, but it only emits in the parts per trillion level. That is a very, very, very low emission of very, very, very highly important in the marine boundary layer. What did we do? We went to a harbor near Cork. That's where I was doing a postdoc. And you can see that here there is a harbor. And incidentally, this is the last harbor that Titanic docked. From there, it went straight into Atlantic Ocean. So this is the photograph of there, and you can see the little seaweed on the shore. So if you look at the seaweed a little closer, there are so many different kinds of seaweeds, but we are interested in something called Laminaria digitata. This is the one, Laminaria digitata. So it has a little holdfast stipe and little blades. Okay. So we went into, so 1% of the dry weight is iodine and accumulated in the form of I- iodides. So we went to the ocean during the high tide without disturbing them. We collected them with the seawater. We brought them to the lab. We didn't disturb them because biologists have a theory saying that when these plants are under stress, then they release H2O2, and then that in turn releases this iodine from the whatever they have in there. So that is the theory. So we kept them in the same sea surface temperature, or not sea surface temperature, sea water temperature is about 5 degrees. So we made a instrument. We have a temperature thermally stable chamber. We have a xenon arc lamp that is an incoherent broadband light. We filter the light. We have 2 mirrors. We made a optical cavity of 75 centimeter long, and then we take the output light, focus into a monochromatic CCD array, it's a detector, which gives you a spectrum of light. And then we made the measurements. First, we made the I0. This is the equation I showed you earlier. Look at the equation, but we know sample. Whatever spectrum we measure is I0. We keep the sample, then we measure I, then we calculate the important broadband cavity enhanced equation, which is called Ipsis equation. We calculate that with the knowledge of accurate. We can calculate the extinction coefficient. We call it extinction coefficient because light lost can be due to scattering and absorption. So we have absorption coefficient and scattering coefficient, and sum of that will be extinction coefficient. So this is the photograph of the instrument. We thermalized using water flow, and this is on the inside. This is the we open the chamber, we can put seaweed in it, and then we can make measurements. And we try to reduce the ozone, because the moment it hits the ozone, you can see, those who are familiar with the spectrum and spectroscopy, you can see that this is the red line, which is derived from the absorption cross section of iodine molecule at a specific instrument resolution, and our instrument spectral resolution is use the convolution of the spectrum to match with the instrument's measurements. So you can see that the red and black dots are the measurements, and it fits very well with the red line, which is absorption cross section of the iodine molecule, which is from the database, University of Mainz database. So you can see that the detection limit is very good, in very small parts per trillion level. Or we changed this into the biology, methane is so many 0.15 nanomole per mole. So we could detect that in every 10-second measurements, and we used 530 to 550, 560 nanometer range, which actually in the top of the graph you can see that converted into wavelength range. So that is in the UV, so that is very high number range. So we calculate the extinction coefficient by using the measurements, and we fit it to a polynomial baseline, that is polynomial baseline, and number concentration multiplied by absorption cross section. That's the spectroscopic technique. Yeah? So number concentration of iodine was we are interested in, and we know the absorption cross section from the database of the iodine absorption spectrum. This was published. So what we found is very interesting. The moment we take the plant and put it in, it's just very high. So very large emission of iodine. Then it relaxes. And as it relaxes, you can see that it put puffs of iodine. Puffs. The puffs are prominent at some time, and eventually puffs it dies off, and we think the plant is dead at that time. And different plant, the puffs are at different frequency. There's no characteristic frequency, but puffs are coming. Puffs of iodine. So I think it's the quasi-oscillatory bursts of iodine, and in the darkness, out of water, I think it is a little stressed, and it is some sort of a biological process that is producing the iodine. Biologists say, I have no idea about it. Anyway, we were very happy that for the first time, we were able to actually make such real-time measurements, very high time resolution. Not only us, other long path, single path optical spectrometers also found that this kind of measurements only triggered us when we make this kind of instrument and measurements. So people have done this across the ocean. They also found 30 parts per trillion of iodine, but they make 1 minute to 10 minutes measurements. Okay, one part. I may go to one or two more quick examples, and then we can stop. So nitrate radical, I said, was very trivial. So 10 to 50 parts concentration in an algorithm. So NO3 is there or not? It's an important question. And NO3 is highly photoreactive. So what we did is that we made an instrument and we took it to chamber. When I say simulation chamber, that's not a computer simulation. That is an atmospheric simulation chamber. That is just a big Teflon bag, and reactions are made inside the bag, and then made measurements. We'll come to that. So we use the same equations, same analysis technique. Only thing is that instead of one number concentration of one compound and one cross section, we have several.